So, welcome everyone to the MathSoc lecture series. So today's talk is by Uri Onn on proofs of impossibility. So welcome to Solomon.
Hi everyone, and thank you for the invitation. So I want to talk about collected few things under the umbrella of proofs of impossibility. When I was a kid and my parents told me not to climb on that tree, I can't climb on that tree. The only thing I wanted to do is to climb on that tree. So when somebody tells you something is impossible, this is very annoying. Like, how can anybody tell you that something is impossible, that you can't do it, or anyone can't do it? So let's start with a few kind of easy examples. This phenomena. So suppose I have a 10 by 10 square, and I want to tile it with dominoes of size 1 by 2. Can I do it? No, right? But now I'm removing one square, 1 by 1. Can I do it? No. No, how did you know so quickly? Yes,
Because the area of the dominoes is always even, but the area of the square is now odd.
Even, excellent. Even versus odd, right? So, if I try to check all the possibilities, it takes me enormous amount of time. And if this one works, if this was 100 by 100, then I'll do those. And whatever computers we will have in 100 years, there will be a number, but they will not be able to solve this by just checking possibility. But we can with a kind of a quick invariant that told us what we heard. Okay, let's try something else. What happens if I'm now removing two squares? Can I do it or not? Yeah.
I don't think you can do it. You can imagine it as a chessboard. And each domino will pile one white square in the black square. But it's something like two white squares.
Excellent. So let's kind of downscale the problem into this 4 by 4, so it will be the color. So I'm removing this one and this one. So the parity argument doesn't work anymore. But if we think about it as a chessboard, then whenever I'm putting one tile, it will always cover one black and one white. And since I removed two black, two of the same color, when I want to put the last one, I can't, because the last one will be similar color. Right here I have 16, but now 8 of one color and 6 the other. And every time I put a domino tile, I cross one of these. I remember 2 of the same color, and I can't put the last. Yeah. Okay. What about now? Thank you. I don't know. But you see, it's a complicated problem. And we need to come with an invariant. We need to come with a clever idea how to see that something is impossible. Otherwise, there are too many possibilities. All right, that was a primary school one. So now I want to upgrade for first year. So here's the next example, which is called Conway's army of peg solidity. So Conway died 3 years ago. He was a British mathematician, then moved to the States. He did combinatorics and number theory and knot theory, and he did many things. Very creative guy, very colorful guy. And he invented the following question. So I have here an infinite board with holes. I draw only if I'm important. You get the point. It's infinite, but there's a line here, and there are holes here, and I'm allowed to put beads in the holes. And whenever I have two beads adjacent and one unpopulated, these are populated and these are not, either vertically or horizontally, I can do like checkers, and I can just take this one, put it here, and remove the other one. I can do it vertically and horizontally. Okay. Now I'm allowing you to put any number of beads below this line. The goal is to go up as high as we can. So let's start to play. So I want to go to the first line. Okay. It's not too difficult, right? I need only two, and I can get the first. All right. What about the second line? Yeah, right?
Yeah, if you go from the side to get that one.
That's right. So I'm putting four like that, and then with one of them I'll go here. Now this will be empty, and I will have something here, and then in the second part I will take this one. So we'll have one here and one here, right? And then I stop, because I raise the configuration of the previous step one step higher. So after these two moves, I got here, and I'm happy, right? Because if I get to if I push up the configuration that already knows how to jump one, then I'm done. Here it's not a big deal, right? But if I have a huge board, then you don't want me to go over all the steps again and again. So it's enough to push up one step. All right. Third one. What do you think? Will that work? So, yeah. Work, right? I will go here. We'll go here. We'll go here. I will have three of these. Then this will be empty. I can come here, and I have this zero configuration raised in one step higher. Right? Looks promising so far. So let's make a small table. What do we have here? So to get to the first line, we needed 2. To get to the second line, we needed 4. To the third line, we needed 8. To the fourth line, can you guess?
16.
20.
Oh.
And for the fifth one,
Maybe 45.
you can't go to the fifth one. Okay. So I want to prove it. Okay, I want to show you that you can't. And again, this is how can I do that? Like, there's an infinite amount of bits that I can put in. My gap would be finite, okay? I will only use finite in n. And I can put anything here to show that it's impossible. How can I do that? I need to go over all the possibilities. Okay, so we need something clever. All right, so what we are going to do, we're going to label. So like in these two examples, we are going to bring something external to the game. I'm not going to show you that there's no algorithm directly, but I'm going to put some invariant and show you that you can do that. So what I'm going to do, firstly, I'm going to decorate the board by symbols. So firstly, I'll show you that you can't reach the fifth one here, just here. So that's enough, right? If I show you that you can't reach the fifth row here, you can't do it anywhere, right? You can start. If you know how to do it over there, we just move the game here. So I'll show you that you can't get over there. Even I can go over there, but it's some your tour guides you can get, but I'm claiming that the bits can't go there. So I'm now labeling the hole. So here I'm putting 1. And here I'm putting x, and here x squared, and x cubed, and I'm continuing this way. And in this direction, I'm putting here x, and then x squared, and then x cubed, and I'm continuing this direction, the same. Now I'm going down, I'm multiplying the row by x. So I have here x, and then x squared, x cubed, x to the 4, and then here x squared, etc. And again and again and again. So I'm multiplying by x when I'm going down, and I'm going to divide by x when I'm going up. So this is going to be 1 over x, and then 1, and then 1, and then x, then x. And this one is going to be 1 over x squared, 1 over x, 1 over x, etc. And over there, there's 1 over x to the 5, which I want to show you that I can't reach that. Okay, so far x was just a symbol, but now I want to give it a value. So, are there any questions? So now, let x be a solution of equation x squared plus x equal 5, equal 1. So in fact, instead of that solution, I want that solution, the positive solution. Okay, let's solve this equation. I think I can do this. Let's see. X 1, 2, that would be minus 1 plus minus square root of 5 over 2. Okay. All right. So two solutions, minus 1 plus square root of 5 over 2, and minus 1 minus square root of 5 over 2. I ignore this solution, and I'm taking this solution. So my x is this number, which happens to be familiar to you?
Is it like golden ratio?
Golden ratio, yeah, or the one over the golden ratio is the kind of common definition. Okay, so this is my x, and now x. Let's observe that x is greater than 0. And x, let's say it's plus 45 over 2, this is less than minus 1 plus square root of 9 over 2, which is 1. So x is a number between 0 and 1. A real number between 0. That satisfies this equation. Okay. So now I want to define an invariant, which is going to be an energy, kind of an energy function. That's the way I want to think about that. Since what do we know about energy? Energy is preserved, but energy is also, you can get, if you look at the system, that your energy can decrease because you get an energy loss, but it's not created. Nothing. So I want to define this E. And what will that be? I'm looking at the state. So the state can be, okay, whatever we had here with the state. Here's the state. I'm drawing now only populated poles. Say I have here 1 and x squared, and then x squared, and then x squared. So the energy of this state will be the sum over all the populated layers. So the energy will be sum of the populated. These labels are not numbers, so I can look at them. And remember, everything is finite. So I'm going to do something infinite in a minute, but the game is fun. Life is fun. We play. So I want to show you that this number does not increase when we play. So the claim is E is non-increasing. Okay, let's check this. So suppose what do I need to check? What are the possibilities? Either I'm looking at 3 poles like this, so I have a decreasing sequence of powers, or maybe I'm playing in the other direction and I have an increasing sequence of powers from here to here, or I'm in this kind of valley where I'm going from x1 to x. Okay, so what happens if I'm in this situation? X squared x 1. So before I play, my energy is x squared plus x. After I play, my energy is 1. It wasn't clever. So in this case, the energy was preserved. What happens if I'm in a situation like x1x? Playing like that. So I will have here, and before I will have x plus 1, and after we have x, and the energy decreased. What's the other possibility? That I'm playing the other direction. So I have 1 x squared, and this one is empty. And before I have 1 plus x, and after I have x squared. Now x is positive, so this number is greater than 1, and x is less than 1, so x squared is less than 1. So my energy decreases. Okay. Now I checked 3 cases, 3 scenarios, but actually covered everything, right? Because if this is now x to the 4, x to the 3, x to the 2, well, I'm multiplying whatever I had here there by x. So that's it. We know that this is it plays the role of an energy function. E is non-increasing while we play. So let's compute the energy at the beginning. And let's compute the energy at the end, potential end, which is 1 over x to the 5. Okay, so right, I want to compute the energy at the start. So whatever you think might help you to go to the 5th line would be any finite combination here. It will still be smaller than the sum over the whole board. So let's compute this. Let's start with the first line. What can I say about this part? From 1 up to infinity. It's the geometric series, right? Oh, one of the few things we know to compute. And it's 1 over 1 minus x. So it's good that x is less than 1. So we can actually compute the whole sum. So this is 1 over 1 minus x. Now I want the other side. So I'll take it twice. And then I'll remove the one which I overcounted. That's the first line. Okay? Now, this is the first line. The second line is x times the first one, and then x times the previous one. So this is also a geometric series. So the first term in this geometric series is the first line. Okay, that's what it is. And then I have a geometric series where my factor is x. X, 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 x. So this is taking this as my first element and then divided by 1 minus x. Right. It's a geometric series that starts with this element. Okay. That's it. We sum the whole. But let's do some manipulation to see what we can. Can you all see here, or should we do here?
No, we can't.
Can?
That works, yeah.
So what do I have there? I have it's 2 over 1 minus x minus 1. So it's minus 1 minus x. And then over 1 minus x. So put in 1 minus x squared. So this is 1 plus x over 1 minus x squared. Okay, what is 1 plus x? I have an equation here.
1 plus 35.
So from here, I can see that x times 1 plus x is 1. So 1 plus x is 1 over x. Okay? So this is here 1 over x upstairs. Now 1 minus x, well, I have 1 minus x here. 1 minus x is x squared. Okay, so, and I have here 1 minus x squared, so that's x to the 4. Which is 1 over x to the 5. So the energy of the whole board is 1 over x to the 5, which is where I want to go, right? But my game is finite, so I don't have enough energy. This is 1 over x to the 5. I don't have enough energy. Okay, so you can't.
How could you like just give energy to each sport?
Sorry?
How could we just give energy to each sport? Is it legal to do that?
So the idea is this: we use whatever we can. So we call it energy because I call it energy simply because it's we call it energy is not included. You can call it weight function, you can call it whatever you want. This is a function which is not increasing, and when you play,
How could we just give like a value to each of the sport? Values.
so I could put here anything I wanted. Yeah, I could put here my phone number and permutations of my phone number. The question is, does it help me? Does it lead anywhere? And kind of this clever choice led to a proof. And you can play with many other numbers that you put here, and that would not give you a proof. So what you learn, you don't learn, because the fact that we don't succeed doesn't mean that it's impossible, right? But so I can put labels, I can play this game, and now we see that we can't go to the fifth row. Okay, so this is John Conway's arm effect solitors, and there are numerous. You can look online. There are numerous variants of that. For example, you can increase the dimension and ask what happens if you play a d-dimensional game where you have a hyperplane, and in one side of the hyperplane you allow to do whatever you want, and how far can you go? You can make it a hexagonal game. There are many variants of this kind of idea.
Yeah, for a d-dimensional version, is there a high enough big integer d so that you can go as far as you want?
No. So for every d, there is a power, yet you can't.
But then I'm assuming if it's infinite dimensional, then you can.
Sorry?
If it's infinite dimensional, then can you go as far as you want?
Infinite dimensional.
Yeah.
Any question? All right, so now I have 3 more stories, with which are of this style, from more serious mathematics. This is also serious mathematics, but kind of this is part of the yeah. And the first one will be familiar to those of you who've seen Algebra 2. Who took Algebra 2 here? All right. So in the next 10 minutes, you can relax. And so a problem from geometry, all the problems I'm going to tell you have the same kind of feature, that you need to show that something is impossible. And in all the examples that I gave you so far, you need to get out of the box. You need to think out of the box in order to solve them. You can't solve them algorithmically. But now, out of the box is going to have another meaning. So at the beginning, it's fairly soft. So here's a problem from geometry. A 2,000-year problem. Open, no, close. Problem. And the problem is to trisect an angle with ruler and compass. So the Greeks, this is a problem that the Greeks try to solve. They play with whatever you can do with a ruler and a compass. So here's the concept of a constructible number. So constructible. So we start with a unit interval. Okay, definitely we have the unit interval. Now we are allowed to create new points. So in a way, there's these 2 points. What are we allowed to do? We are allowed to, whenever we constructed 2 points, we can draw a line with a ruler between these 2 points if we are allowed. And whenever we have 2 points, we are allowed to draw the circle with that value. These are the allowed operations. Okay, and so for example, you can do many things with it. You can, firstly, if I have these 2 points, I can go indefinitely by drawing this line. My ruler is infinite, and now I have my compass, and I can draw a circle, and then I can draw a circle here, so I can create the integers. Okay. But I can also have with an interval into 2. If I have an interval, it could be the one that I started with, but it could be a new interval that I already constructed. So the only point is that these are 2 constructible points. I already constructed them by intersecting circles or intersecting straight lines or a circle and a line. I can take my compass and I can draw a circle here. I'm allowed. I can take it and draw a circle here. I'm allowed. And then I'm joining these 2 points. And I did 2 things here. First, I partitioned this segment into 2 half the segment. But also now I know how to find a perpendicular to a given line. So whenever I have a line, I have a perpendicular. So immediately I can now have another axis here and have integers here and integers here and integers here. So I have all the integers. All the integers are easy points. But I can also, for every 2 points that I have here, I can half them. I can do things like that, but I can do much more. I can actually half an interval to any number of points. What will I do? So suppose I want to partition this interval into 3. So I will have a perpendicular here and another and continue here. And then I will draw this line here. And then I will draw parallel. So we need to check it using the compass and ruler. You can draw a parallel, or you can copy an angle, and then there you are. Here's your third. Right? And so I can, with this way, I can generate any all the Russian numbers are here immediately. So all the Russian numbers are constructed. And you can do more because we have circles, you can solve quadratic equations, so you can take a square root. You can do many things. You can half an angle by you have your point here, you draw a circle, now you have a segment here, now you can take the perpendicular to that segment here, and that will give you half of an angle. And now the Greeks ask a very natural question. You have an angle, can you bisect it? Can you find lines which you can construct it, right? So when I'm saying I can find lines, it means that I need to be able to construct a point on that line and on that line, and so that I can draw these lines. So they wanted to know if they can bisect an angle. And they try hard, and they couldn't. And that was open for 2,000 years. And the solution, and so indeed you can't. All of you. No one. And the solution is using algebra. So the thing that I'm bringing from outside is algebra, and those of you who will take algebra 2, you will show that the constructible elements form a field. So I already showed you that the rationals are in. And I'm telling you that you can, if I had more time, I just want to touch it in other subjects, but you can find the square root of the segment by cleverly playing with circles on a similar triangle. And you can show that the constructible numbers, they form a field. Like if I'm just looking at the one-dimensional thing, it's a field. And then you need the first 2 weeks in algebra 2, you really don't need a lot. So all of you who took, algebra, and know what a field is. If we talk about that for 15 minutes, I will give you the arguments, maybe half an hour, just to be relaxed. All the arguments for a problem that the Greeks couldn't, or nobody could solve for 2,000 years, which I think is quite impressive. Okay, it's not possible to trisect an angle, but what do I mean by that? Let me be more precise. Of course, I can trisect an angle. Look, here's an angle. Look at this 270 degrees here. And continuing this one, and continuing this one. Here, I just trisected an angle. The point is, yes, there are specific angles that you can, but there's no algorithm. There's no algorithm that I'm giving you an angle that you can trisect it, because there is one angle, 60 degrees, that you cannot. It's I mean, there are more, but it's enough to show that there's one angle that you cannot, and that's kind of takes the block. There's no algorithm, because if there was an algorithm, then you could do it forever. Questions? Okay, that was my geometry story, not mine, but a geometry story. Something from algebra, which you also see in algebra 2, is the fact that you cannot solve quintic with radicals. So, Galois proved that one cannot solve quintic using radical. So what does that mean? When I have I just now use, when I have a quadratic, I can write down the solutions. And using these, using coefficients and roots, here on the square. So this is a radical, this is called a radical. So for x cubed, there is a formula, and also for x to the 4, but not to quintic. So if you have a quintic, there is no formula. Now again, there are specific things that I can solve. Okay. X to the 5 equals 32. I can do. Yeah. There are things we can do, but there's no formula that will solve any of them. All of them. How do you prove that there's no formula? So this is kind of the genius Galois. What he did, he connected solutions and radical solutions to group theory, And then it was able to prove by properties of coming from group theory that you cannot find a solution to every point. Galois 8 died. I don't know how many of you know the story of Galois. It's a massive story. Died when he was 20, very young. So whatever he did, which we call Galois theory, he did by the age, by the time he was 20. Okay, so this is another story about impossibility showing up in algebra. And now I want to tell you another one, which was quite a shock for mathematicians when it was discovered. And this is the incompleteness of arithmetic. Gödel's incompleteness theorem. So Gödel, I think it was something like that. And in 1931, when he was 25, he wrote a short paper, and I don't remember the title, but it's about the incompleteness of certain systems. That was the title. And the idea, so he proved that, so all of you know what piano axioms? I do. And stand. All right. So piano axioms is the axiomatization of arithmetic. So when I'm saying arithmetic, I'm talking about the natural numbers and addition and multiplication. So that's what arithmetic does. So we have the natural numbers, we add and multiply and we ask questions. Is a number prime? How many twin primes do we have? Twin primes is divided by 2. Is every even number a sum of 2 primes? This is questions from arithmetic. Everybody can understand questions. And the answers are usually very difficult. So that's the object of study, and there's the axioms. Similar to what happened in Euclidean geometry. So Euclides, he wrote the 5 axioms and wanted to show that everything follows from these axioms of deduction. By the way, there are many holes in these axioms, if you think about it, but they were corrected. So there's a bit more axioms in order to frame geometry. But that idea kind of prevails in mathematics. We have axioms for every theory that we have a language. Here's my language is class and application, and the language can have predicates and parentheses and maybe quantifiers. So this is my language. And then within this language, I can write axioms. For example, one of the axioms of the natural numbers is that there is a successor function. And you can guess what it is. So it says that every element has a successor. You need an axiom for it. You want to do it in an axiomatic way, kind of have a set of axioms that prove everything. You need some axioms. So, for example, there's an axiom for every x. So our world is the natural number. I mean, this is the model that we have in mind. And for every x, s of x is not 0. That's it. So the zero has no nothing before zero. So this is an axiom. Okay. Another axiom is that for every x in every y, if the successors are equal, then the numbers are equal. Okay, this is another axiom. So there's a list of axioms which describe arithmetic. And Gödel proved that there exists. Now this is really outrageous. There exists statement let's call it G together, such that G cannot be proved. So what does it mean? I have my axioms and I have deduction rules, and I can prove theorems. For example, here's a theorem. This is a theorem, right? 1 plus 1 equals 2. This is a theorem, right? Because I only have the definition of the successor of the next one. How do I know that the successor of 0 plus the successor of 0 is the successor of 1? It's not one class. Okay, that's a theorem. You can prove. So, and there are many theorems you can prove. Maybe that looks interesting, but you can prove theorems using the axioms. So, Gödel shows that G cannot be proved. The negation of G cannot be proved. Okay? The statement, which neither G nor the negation can be proved, but G is true. There's a statement. So, take a minute to appreciate. There's a statement. You cannot prove it. You cannot prove its content, its negation. But it's true.
Oh, sorry, does that just mean that you don't know what G is? Because if you knew what G is, then it's the proof.
No. Get it constructed.
Oh,
Yeah. So let me tell you a little bit. Okay, now, but look, what's the distinction here is that a proof is a finite system, is a finite list which you have axioms and then you have reduction rules. And you use the axiom, then you use previous theorems that you prove. At the end, the last line is the statement. Okay, that's a proof. That's a proof. It's a finite score. So there's no proof for G, there's no proof for negation, but still G is true.
no.
Okay. So just for that, you know, we need to explain a lot of things. You need to explain what does it mean to prove something. What is a proof? Okay, you need to formalize all these things. And what does it mean to be true? Okay. So let's kind of play with the ideas a little bit of what Gödel did. So for me, this is kind of it's the extreme example of something which is impossible. Really tells you there's statements that you cannot prove, but they're true. So what did Gödel do? And again, now that has the flavor of coming out from outside into this language. So there's language here, there's a theory here, the axioms here, but you need to come from a different direction. So here are some flavor of what it is. So some ideas. So what he did, he played with it starts with easy paradox. So this is something you all know. And this sentence is false. Okay, so is it true? Well, if it's true, then it's false. If it's false, then it's true. So this kind of silly paradox, Gödel made it something concrete. So he replaced this sentence by saying this statement cannot be proved. So here there's no paradox, right? This statement can be true. So I'm distinguishing the validity versus provability. So this sentence statement cannot be proved. So this is one of the ideas he played with. And another idea goes back to something which is called the Richard paradox. He was a French mathematician, and here's what he played. So imagine that you enumerate all the statements in arithmetic. So, for example, properties. So say say sum of two integers. So this is a property. 2 satisfies this, and 3 doesn't. A multiple of a number by itself. So kind of a square, yeah, that's what I mean by square. But we're only in arithmetic, so this is only natural numbers. So, for example, 2 will satisfy this one, and 15 will not satisfy this one. So now I'm enumerating all the statements. So every property that you can think about will have some finite length. Now order all of them by the length, and then maybe the cryptographic order to refine the ordering. So you can enumerate all the statements. And now say this number maybe 15, and this number maybe 2. And I'm continuing this way. And now define. So now the label might satisfy this property or not. Okay, so a Richard number is one that such that the label doesn't satisfy the statement. Okay, so 15. What is it? Is it a Richard number? It is, right? The label is 15, but 15 does not satisfy this. So 15 is a Richard number. 2 is not a Richard number because we have 2, and 2 is even. Okay? So now in this list, there's the definition of a Richard number. So somewhere here, there's n, and then n labels be a Richard number. Now, this n, is it a Richard number or not? So a Richard number is a number that doesn't satisfy the property. So if n is a Richard number, then it doesn't satisfy this property, so it's not a Richard number. But if it is, you see, it's the same idea, except that it's kind of, it looks like this, yeah, it looks like this. So the solution to Richard paradox, and I'll finish in 2 minutes. So the solution is that this is not a statement which you can formulate using the language. Okay, so this you will never see this in your list if you go by the rules of the thing. And the ingenuity of Gödel took this idea and he actually put it into practice. So what he did, he labeled all the statements in arithmetic in a very clever way, such that such a statement which we call meta-mathematical, which means I have my language, I have my theory, I have my rules. This is the axiom. That's what I have. That's what I have. Only these symbols, only this quantifier, only that. I can write whatever I want, but only with this one. And here is a statement which cannot be formulated using this language. But what Gödel did, he managed to write down a statement like this. So he enumerated everything, and he managed to translate such a statement back into arithmetic. Okay, so this is also something which is meta-mathematical in the sense that it's not clear how to phrase this using the arithmetic language, but that's what Gödel managed to do. So he labeled all the symbols and all the statements, and then he interpreted the numbers as statements, and so he played a very, very clever game to take these kind of statements which come from outside and bring them back into arithmetic and show that there are statements. If you cannot prove them, rather than negation,